from the end of the 19th century through to the beginning of the 21st century, and discuss the slow development from classical thermodynamics of quantum information theory, and specifically characterizing quantum information theory as a new kind of physics that describes systems that are exchanging finite amounts of discretely encoded information across some intervening boundary. And so we use this very conventional graphical notation of two agents or physical systems, Alice and Bob, A and B, that are exchanging energy and information across some boundary. And I always use a blue ellipse like this to indicate the boundary that separates Alice from Bob. And this new approach to physics is entirely topological. It's not geometric. So it doesn't assume a particular background space-time. So it doesn't assume that Alice and Bob are spatially separated. And so this makes it a very different kind of theory from classical information theory, in that the channel that separates Alice from Bob, this boundary, is a boundary in state space. It's not a boundary in some geometric embedding space, and in particular, it's not a boundary or a channel that's embedded in a three-dimensional space that separates Alice from Bob. We can write down an entropy, and the limiting case of that entropy is the entropy of a black hole, the densest possible encoding of information in space or on a boundary. And this holographic principle allows us to see any boundary, as we discussed in session 1, as an encoding of bits. So the previous boundary of these in qubits, we can think of as a holographic screen. Now, why is that important? It's important because it allows us to use this idea of holography and this idea of a fixed encoding of a message or a fixed encoding of an observable entropy at some density that was developed in cosmology to talk about arbitrary quantum communication channels. So we can import a whole bunch of theory that was done someplace else into quantum information theory and see that it works perfectly because it describes exactly the same situation. Now, what does this tell us philosophically? It tells us that Alice and Bob can learn about each other at most n bits per communication cycle. So the maximal amount of information that they can get from an observation is the n bits that the other one wrote on the screen. So this tells us something very important, that when an agent is looking at their environment, which is this other agent, Bob, the amount of information that can be extracted from the environment is actually proportional to the size in bits of the boundary. And the holographic principle just makes that size finite in space. And I said early on that there's no embedding space-time in this theory, that Alice and Bob are not thought of as separated in space. But as soon as we use the holographic principle, we can think of the boundary between them as having a spatial coordinate, even though they don't have a spatial coordinate. So we'll get back to this point in September when we talk about theories of emergent spacetime. But all of these theories of emergent spacetime come back to this idea that boundaries can have spatial extent, even though the systems that they separate don't have any natural spatial description or natural spatial degrees of freedom.